Hi, everyone. My name is Chan Ho. I work at Quora. So today I will be discussing how we build Quanta. Quanta is Quora's counting system, which is built on top of HBase. I will be discussing this with Nikhil. So quick show of hands, anyone has used Quora before, heard of Quora before? Cool. So Quora is a knowledge platform on which you can ask any questions, and the system will automatically try to figure out who is the best person to answer questions. And we have any topics under the sun pretty much, ranging from rocket science to quantum mechanics to things like parenting and anything in between. So our mission is to grow and share the world's knowledge. We are fundamentally believe that for majority of the knowledge in the world, they are pretty much trapped inside people's head. Maybe you do not have access to books in some library. Maybe you don't have access to some journal papers because this is too expensive. Maybe it's just because you cannot talk to the people you want to get the answers from. So we fundamentally believe that by building Quora, we can make this happen so that you can ask any questions and people will answer them. For example, who will be the best person to answer about this particular TPP thing? Probably Obama. Yeah. So if you want to ask about how do you want to make Kafka and Zookeeper to work together, you also could be able to find answers on Quora. So here is an example which a committer of Kafka actually answers a particular question. And a lot of people probably live in the San Francisco and maybe work in some other cities in the Bay Area. So you will know about how you can make better use of your time. This is a good question to read about as well. So our mission is grand. So we make some progress already, but there's still a long way to go. But to give you some insights of how we have achieved already, we are at around 200 million monthly uniques. There are millions of questions and answers on the site. And there are hundreds of thousands of topics that you can browse about. And we have a very lean team, actually, which is less than 100 engineers. But this we have achieved pretty much. We have a pretty big achievement, actually, right now. Here's an insight, an overview of how we make use of how we build Quora on the cloud. We are at to support that at scale, we have to support pretty much 1 billion real-time updates and RISP every day. So here are some examples of users of Quanta, including content views, ads, and some internal dashboards. So in the following talks, we will be discussing the design constraint of the system, and then the update algorithm, and how do we design the architecture, how do we achieve horizontal scalability, and also discuss some alternatives out there. So first off, design constraints. Here's an example product of Quora. So as you can see here, this is a way for you to look at your performance of each of your answer, in particular, how many views you get. As you see, there, each of the views actually correspond to a single counter on Quora. So here are a bunch of design constraints which are implied from the product requirements. You don't want to lose an update when the server is restarted, right? So that's important to have an explicit commit point after which the updates are pushed. We also want to maintain a billions of counters, like I said in previous slides, that we are at scale, that we cannot be bounded by a single machine. So we have to design a system in a way that could be scaled easily. We also have a very high volume of read and writes. So right now we are looking at 100K of writes per second and a million reads per second. So we immediately imply the following set of constraints. So we want to have persistence on this, which are resilience to restarting of processes and that kind of things. You want to be able to scale across different machines. You want to achieve high volume of throughput. So we implement append-only writes. So let's take a closer look at this stats product. As you can see here, we have a bunch of counters which are kind of related to each other. So it is important that we can achieve low latency of risk of counters which are kind of like related to each other. In particular, we want to avoid random reads on the same request. So we want to have some way to batch the reads together On top of that, we also do aggressive caching so that in most of the time, you're not hitting the disk when you read some counter data from Quora. Another thing is that we actually store this these kind of counters in a range sorted format so that you can easily do batch query very efficiently. Writes shouldn't be lagging behind by too much. So we actually allow writes to be lagging by a little bit, but probably it's not great that it will be lagging by like 10 minutes. So which means that writes can be asynchronous. Another thing is that this kind of counter should be highly available, meaning that you cannot afford to cause site downtime when this risk is too expensive or write is too expensive. In order to handle 2x loads, we should be able to just throw in 2x more resources, like 2x more machines, 2x more memory, and that kind of things. And the system should be ideally designed in a way that can be scaled very easily, up to 220 to 50x. Operational cost should be as cheap as possible so that engineers don't need to mess with things whenever there are any problems with Quanta. So let's take a closer look into another aspect of the counting system, which is aggregation. So at Quora, we want to support arbitrary time bucketing, meaning that you can query things like how many times this particular event has happened at every X in the last Y. A quick example is weekly counts built on top of daily counters. But as you can look at here, if you query the last week counts, which is built on top of every single daily counts in the last 7 days, then if you query the counts at the beginning of Saturday, let's say, then you will be interestingly looking at around 1 divided by 7, which is around 14% of percentage error. So this is not great. So this kind of worrying error is actually fundamental to the way how you are going to implement things. So it is important that if we can allow our users to specify how many buckets they can specify for their rolling Windows counters, then they can have some way to configure their rolling errors. Another thing we want to build for Quanta is for supporting dynamic aggregation. So here's an example. Each of the AID counter here correspond to answer views, and each of the UID counter here correspond to the user level view. So for example here, the UID counter is basically the sum of all the direct counts at each AID level. So whenever the AID level counter is updated, we want to propagate the updates to the UID level counter as well. At the same time, we want this kind of aggregation to be dynamic, meaning that once an edge is removed from the graph, the counter should be updated correspondingly. So an example here is that if you remove the edge between AID2 and UID, the direct count of AID2 should be subtracted from the UID level counter. So here's the idea. An example use case of Quora is you might have a UID counter which aggregates across all the answer level views. And this is also great that if we can support arbitrary directed acyclic graphs. So any graph like that, we should be able to support aggregation correspondingly. So next up is the upgrade algorithm. So there are mainly two classes of update algorithms you can consider. One is lazy update, the other is eager update. The main idea is that for lazy update, you just want to query the aggregation count at the query time. But for eager update, we want to avoid the time you need to read the graph when you query the aggregation counters. It turns out that at Quora we need eager updates because we just have so many traffic, and doing a lot of processing at query time is not great. So we want to pre-compute as much as possible before you actually query the counts. So this is an overview of the core algorithm of Quanta. Basically, you have to support two kinds of operations. One is increments, meaning that whenever an event happens, you want to increment the corresponding counters. The other is the HH operation, meaning that you want to say that now that this counter should be associated to another counter, and you want to make it so that the direct counts and the total counts are consistent with the graph structure and the direct count stored on the system. So I skip over the V1 because of time constraint. So let's inspect a little bit of how the V2 algorithm works. So as an example, maybe you can quickly think that whenever you want to add an edge from node U to node V, you can simply read all the direct counts from all the ancestors of U. Meaning that, for example, here you want to add an edge between B and C, and you want to update the total count of C as a result. So something you can do is to try to look at all the descendants of B, which is A and B, and then query all the direct counts and sum them up, which is 1 plus 1, and then propagate them to the total count of C. So it seems to work in this case. However, this algorithm actually will fail on a particular graph structure called diamond. So what will happen if we add an edge between C and D in this case, following the algorithm? It turns out that you will be adding the direct count of C and direct count of A to the total count of D, which is A plus C. And if you look at what is the results, it turns out that A is double counted, and we want to fix this bug. So an update algorithm to fix this problem is to still read all the direct counts of all the descendants. Sorry, excuse me. So you still want to read all the direct counts of all the descendants of the from node to the to node, but at the same time, you only add that if and only if the node is not already an ancestor of the node. So here, because A is already a descendant of D, so you do not want to cause double counting. So basically, you want to discard A when you update the total count of D here. So here's the final graph of the algorithm, which solves basically all the issues. For each of the ancestor of U, and for each of the descendants of V, you check whether or not the descendant node is already a descendant of the target node. If yes, then you disregard that. Otherwise, you will update the total count with the direct count of that. If you do not completely get the idea, it's fine as well. But the takeaway is that you want to avoid double counting. So basically, you do a pairwise comparison of each pair of ancestors of U and descendants of V. If such a pair of node is already has a path in between them, you will disregard the update. As it turns out that another important properties of this graph of the algorithm is that it turns out to be commutative. And there's a mathematical way to prove that, but we do not have enough time to go through that. So, but this is one important property that we can make use of to implement our system. So as long as the resultant graph after processing all the graph updates will be correct, you can switch whatever order the way you want to process those messages to. And it's turned out that we can make use of this property to implement our Quanta system very efficiently. And next we'll be talking about the architecture.
All right, so far we understand what we want Quanta to do. We understand what is the algorithm, how we actually make it happen at scale, what is the architecture behind Quanta. So there are 5 parts of Quanta. One is a journal, one is a client, one is a processor, one is a graph store, and one is a counter store. So you can think of client as a very thin wrapper sitting on all our machines, let's say a client machine. And all it is doing is when an event happens, it publishes a message to a journal. Journal is just a message bus, a persistent message bus. And then a processor pulls data from the journal, processes it, has access to graph and counter stores. These are databases that store the counting data and the graph data. Both of these stores are built on top of HBase. So processor is pulling messages from journal, doing some processing on them, doing some reads and writes on both counter store and graph store, and then calling it a day. And if, let's say, client needs to access some data, they directly skip all this machinery and go directly to, let's say, the counter store. So writes can lag behind because they might take some time to come to the whole pipeline, but clients can always directly access the graph store and the counter store. So let's go through all of these in more detail. So client is a fairly simple thing. It's not doing much. All it does is publishes message onto the journal. Messages are always in a language agnostic, let's say, thrift format. So clients can be written in any language. You can write clients that are all contributing data to the same table. That's possible too. And it also knows how to read data directly from the counter store. And so it understands what's the API for counter store and how to process or pre-process rather the input into the counter store query. Fairly simple thing. Journal is basically a replicated persistent commit log. And once you put messages to it, it guarantees that messages are never lost after that point of time. They are stored temporarily till processor has the time to come to these messages and process them. And once processor is done processing them, it will update the checkpoint. And after that, the journal can remove these messages. We provide at least once processing semantics at the level of journal. And then in processor, we try to make it idempotent, so it becomes exactly once. We'll talk about that a bit later. And any persistent commit log could have worked. We chose Scribe in the beginning because it was easier to use, though it's not the best choice given that it's somewhat lossy. And we are currently running on Kafka. Processor is the real heart of the system. So what it is doing, first of all, it is reading updates from the journal. It is processing them in batches by reading and writing to both graph store and the counter store. Graph updates can also be processed in batches because the updates are commutative after all, so you can reorder them and batch them in any order you want. And so what we do is we take 2 large scans of BFS on all the relevant affected edges. So one downward BFS scan to understand all the descendants of all the relevant nodes, and one upwards BFS scan to understand all the ancestors of all the relevant nodes. And this idea of processing updates asynchronously in batches is the single most important idea in the whole design. Everything just follows from that very naturally. What do I mean by that? So first of all, processors become stateless if you're doing asynchronous processing. And so we don't have to worry about the availability of processors at all. They can come and go, and we won't really care about them. It also means that it's much easier to absorb spikes. Like most other consumer products, there's a big variance in max and average traffic on Quora. And so if let's say there's a spike, we'll probably have a lag, but at least we won't be going down. And so that part is very useful as well. Given that you're processing data in batches, few more things become possible. We can now deduplicate events that are, let's say, very hot. So for instance, if a counter is incremented by 5 times, instead of making 5 different calls to the underlying stores, we can just say that increment this counter by a number of 5. And so there are some counters that are very hot, and so we can deduplicate them. We can also batch all the IO requests to underlying stores. And that's very important as well, because a lot of time is just spent in simple IO, not the processing. It can also do some optimizations based on the graph structure. So if let's say we need to do certain BFS, by looking at, let's say, the state of certain edges, we can completely cut off certain queries because you know that they just won't have any edges next to them. Currently, it is implemented as a system of minutely crons. In fact, the lag of a few minutes that Chanho described earlier is precisely coming from the fact that it is running every minute. We could make it, let's say, run every second, every 10 seconds as well, and we could reduce the lag. Why did we choose a system of minutely crons? That sounds like a relatively frail system. We chose that because we could. It seemed to work reasonably well for our use case, and it was very easy to use that. We do plan on moving to Spark streaming at some point of time, but so far we haven't felt the need to doing that. Okay, so let's talk about CounterStore. CounterStore and GraphStore, they are both built on top of HBase, and that is why we are here in this conference today as well. In fact, it's probably easier to just look at the schema. So this is what the schema of a counter table would look like. You have a counter represented as a single row in this table. So a row key is corresponding to a counter here. You have different types of time windows in which you can do a query. So queries in last hour, last day, last week, a daily time series. All of these windows are their own column families in the system. You have multiple columns in these column families. The columns correspond to a fixed chunk of time. So if let's say you're doing a daily time series, then a single column corresponds to a single day worth of data. If let's say you're doing last hour time series, that is 3600 seconds, and you want to have a rolling error of 1%, you divide it in 100 buckets, and then each column in this column family would be a chunk of 36 seconds, and that's all we need at that point of time. So why did we choose HBase? So HBase is really good for write-heavy workloads because it does append-only writes through write-ahead log, so that is really good. We also want to be able to query related counters efficiently. And since HBase stores data in a range-sorted format, we can design our counter keys in a way that related counters are close to each other on the disk. And so a single disk seek is sufficient for our purposes. It supports variable number of columns. That's also always good because we are using variable number of columns for different windows. And more importantly, it can automatically garbage collect older data for us. So we don't have to worry about writing anything that removes columns that are not relevant anymore, because let's say they are not in the last hour period anymore. We have also found that bulk upload is very useful for our system. This is something that, to be honest, we did not appreciate going into the project. But at some point of time, we realized that the system was powerful enough to handle incoming volume of data. But to go back and restore the 5 years worth of data into Quanta was just not possible in an online fashion. And that is where bulk upload came into our rescue. And we also wanted very high availability of Quanta reads. But since clients are directly talking to Counter Store for reads, as long as Counter Store is highly available, reads would be highly available as well. And since HBase supports multi-way replication, that design constraint is also met by choosing HBase here. What about Graph Store? So Graph Store is also built on top of on top of HBase. We built a general purpose system called as Graphic. I guess it's somewhat similar to Zen system from Pinterest that we were hearing about earlier. Conceptually, you can think of it as storing data in a sparse adjacency matrix. Every node in the graph is a row, and every node in the graph is also a column. And if there is an edge between U to V, this cell has some data. Otherwise, it's just not stored in the system. We have two column families, one for incoming edges and one for outgoing edges. This way, we can do both ancestors and descendants of a given node if we really needed to. And one of the reasons why HBase is really good for this is because we are doing a lot of traversals on this system. And traversals usually end up, let's say, at the edge of the graph, beyond which there are no descendants or no further outgoing edges. And you still want to find out, let's say, outgoing edges at that level. And since HBase uses Bloom filters, it can answer negative queries extremely efficiently without going to disk at all. And this cuts down traversal time by a lot. Okay, so this is what the architecture looks like. I have described each of the pieces individually, but how are they fitting together to give us horizontal stability? So we knew early on that sharding processor is something that we would have to do. We just cannot handle all the throughput that we need from unsharded processor. But sharding is not easy because there can be race conditions. So why would there be race conditions? So this is the algorithm that Chenho described earlier, a simplified version of that, but still you will get the idea. All the things in purple are talking to the counter store, and all the things in red are talking to the graph store. And something is highlighted if it is, let's say, doing a write, and otherwise it is just doing a read. So you would see that increment algorithm and the graph add edge algorithm, they're talking to both counter store and graph store. And in one case, one of them is doing a write, another is doing a read, and the other one is doing a write for the second store, and the first one is doing a read in those cases. So if we just to parallelize these naively, we would clearly run into race conditions because the resource ownership is not clear in this condition. So how do we handle that? We can make few more observations about this. So one observation is if counter updates are running in parallel, they do not together create a race conditions as long as all of your increments are atomic. So they are not the problem with themselves. It's the counter updates and graph updates together that create a race condition. The second observation is the volume of counting updates is way higher than the volume of graph updates. Why is that? Every time someone is coming to Quora, we are generating large number of, let's say, counting updates probably. But graph updates happen only when, let's say, a new answer is written, or let's say only when, let's say, a new user comes to the product, or only when, let's say, a new ad campaign is created, things like that. And they're extremely rare. So we can make one sharding solution out of it. Solution is simple. Partition processor in two independent parts. One of them is doing counts. Partition that further is as many shards as you want. You have a single shard for all the graph updates, and they're coordinated through a system of exclusive shared locks. So all the counter updates have a shared lock, and the graph update has an exclusive lock. That kind of works out. Graph update volume is low enough. It's not a problem. But one problem that we did find in this was as the number of counter shards increases, there's a lock starvation happening because the graph update just does not get to execute at all. And also, we just want to eliminate locks. Having a real-world distributed system with locks in it is generally not a good idea. So we need to find a way to shard it further without using locks and while eliminating race conditions. So one more observation is all the connected components of the graph are completely independent of each other. If let's say you have two different components, there is just no way their queries can go affect the same rows in any either graph store or column store. And so if let's say we could somehow identify all the connected components of the graph, we can put them on different processors, and then it would all work out. And so this is a solution. What if we co-shard both counting and graph on connected components and then put them sequentially behind each other. That is, application owners define a sharding key for us. They do that on the basis of their understanding of the application graph. In this case, let's say a sharding key could just be the UID who's writing all these answers, because they would never have collision with different user. And we can now map all the updates of a single connected component to a single logical shard. And we can say that that logical shard is certainly executed by a single physical shard. And within that physical shard, graph updates and counting updates are run sequentially one after another. So they don't create a race condition with themselves either. This works out. It's just that connected components is a much stronger condition than we actually need for this to work out. We know how to provide out-of-box co-sharding for all cases independent of connected components. We have not built that yet, because in practice, all the graphs that we have dealt with do have very clear connected component structure. But we know how to do this if we really needed to. Okay, so far we have told you about what Quanta is all about. We did consider alternatives as well when we were getting started. So, and even though I'm presenting this towards the end, that does not mean that we looked at these alternatives and we were done. We actually look at when we were starting, but now we are presenting them in the end, just so that it's easier to understand what we are talking about. So Twitter has talked about a similar system called as Rainbird. It was supposed to do distributed counting with aggregation and temporal bucketing, very similar to Quanta. The main difference was it was only doing static aggregation in the graph, not dynamic aggregation. What does that mean? If, let's say, an edge is removed in the graph, they would not want to go back and change the data. In fact, the graphs were just not supposed to be dynamic at all. And this was one deal breaker for us. Also, they had a fairly high latency. The reads were around 100 milliseconds, whereas you wanted our reads to be around 1 millisecond. So their solution was just not good. If you're interested, they built it on top of Cassandra, whereas we did not have Cassandra support at Quora. And so this was another reason why we didn't want to choose this. LinkedIn has also talked about a system called Pinot. This is, as it so happens, is also powering a lot of similar features for LinkedIn, views and who's looking at your profiles and stuff like that. It has a nice SQL layer on top of the actual database. So there's a nice query engine. We would have loved to get that, would have made certain analysis easier, but it had way too many moving parts. And we felt that for our team, if we, let's say, adopted this, there would be a very high operational cost, and we just did not want to have that. Facebook has also talked about a similar system. As it so happens, it's a common problem. Facebook has also talked about a similar system that is almost identical to Quanta. It does similar graphical aggregation as well as temporal bucketing. In fact, it's using similar technology as well. It was built on top of HBase and Scribe when it came out. Except, similar to Rainbird from Twitter, it also only does static aggregation, no dynamic aggregation anywhere. But still, a lot of our design choices are inspired by this system. We just took this as a starting point, added dynamic aggregation on top, and then let all the changes trickle down in the whole design as that was happening. Okay, so in summary, Quanta is a service that is built on top of HBase, which can do counting along graphs which are dynamic in themselves. It supports defining arbitrary time windows, as well as configurable rolling errors on those windows. It has a very low read latency of around 1 millisecond. It was doing around 1 billion updates and reads every day when it was first created. And the design is set up so that we can go to 20 to 50x if we needed to. And it is powering all the ads reporting, all the features based on content views. A lot of machine learning based count features are also migrating to Quanta, and many other systems are currently in migration. I guess that's all. Any questions?
Okay, we have time for a couple questions, but we're cutting into your break now. So we'll ask a couple, and then I'll let you guys flog the speakers on your own time.
So 2 questions. How do you keep the counts idempotent? And what if you need unique counts, like how many unique users visited a question? How do you uniqueify?
So the first question is, how do we keep this whole process idempotent? So we use HBase versioning for that. What we do is we take the checkpoint in the Kafka journal and make that as the version in the HBase update. And so if you have to repeat the same thing again, we'd either end up using the same version or a lower version. And if the version is higher, that means it is indeed a fresher update. And to your second question, how do we count unique number of users? We do not do that. We did consider using something like a hyperlog type of structure in which we can do unique counting in an efficient format, but that's just not required right now. Thank you so much.
Thanks.
Sure, yeah.
You said the latency is 1 millisecond. Is this average latency or
I think this was
1999,
I think this was
percentile?
P95.
95%? How could you do that?
We have a very
this
thick
for
memcached
read or
layer in
write?
front of this. This is for reads.
For read, okay.
Yeah, for writes, like latency does not make sense because it is an asynchronous process. But for reads, we have a very thick in-memory caching layer. So very few read requests actually go down to the HBase level. And even then, I think the way it works out is it has a very, like the block cache on HBase level also is very effective here because it has a locality here that is employed in this, if that makes sense.
Okay, thank you.
All right, last question. This side of the room didn't get a chance.
So what is the average latency when the request is going to HBase?
I don't think I have a number on that.
Oh, okay.
But I would imagine that it's also not more than a couple of milliseconds.
Okay. In tens of milliseconds?
Couple
or-
of milliseconds, also. Less than 10 milliseconds.
Thanks.
All right, thank you very much.
Cool.